In mathematics, a simplicial complex is a set composed of points, line segments, triangles, and their n-dimensional counterparts. See illustration. Simplicial complexes should not be confused with the more abstract notion of a simplicial set, appearing in modern simplicial homotopy theory. The purely combinatorial counterpart to a simplicial complex is an abstract simplicial complex. Definitions. A simplicial complex, K, _mathcal K, is a set of simplices that satisfies the following conditions. 1. Any face of a simplex from K, _mathcal K, is also in K, _mathcal K. 2. The intersection of any two simplices, sigma 1, sigma 2, K, _sigma_1, sigma_2 in mathcal K, is either empty set or a face of both. Sigma 1, sigma_1, and sigma 2, sigma_2. Note that the empty set is the face of every simplex. See also the definition of an abstract simplicial complex, which loosely speaking is a simplicial complex without an associated geometry. A simplicial K-complex, K, _mathcal K, is a simplicial complex where the largest dimension of any simplex in K, _mathcal K, equals K. For instance, a simplicial 2 complex must contain at least one triangle, and must not contain any tetrahedra higher dimensional simplices. A pure homogeneous simplicial K-complex, K, _mathcal K, is a simplicial complex where every simplex of dimension less than K is a face of some simplex, sigma K, sigma in mathcal K, of dimension exactly K. Informally, a pure 1 complex looks like it's made of a bunch of lines. A 2 complex looks like it's made of a bunch of triangles, etc. An example of a non-homogeneous complex is a triangle with a line segment attached to one of its vertices. A facet is any simplex in a complex that is not a face of any larger simplex. Note the difference from a face of a simplex. A pure simplicial complex can be thought of as a complex where all facets have the same dimension. Sometimes the term face is used to refer to a simplex of a complex, not to be confused with a face of a simplex. For a simplicial complex embedded in a k-dimensional space, the k-faces are sometimes referred to as its cells. The term cell is sometimes used in a broader sense to denote a set homeomorphic to a simplex, leading to the definition of cell complex. The underlying space, sometimes called the carrier of a simplicial complex, is the union of its simplices, closure, star, and link. Let K be a simplicial complex and let S be a collection of simplices in K. The closure of S, denoted CLS, is the smallest simplicial subcomplex of K that contains each simplex in S. CLS is obtained by repeatedly adding to S each face of every simplex in S. The star of S, denoted Saint S, is the union of the stars of each simplex in S. For a single simplex S, the star of S is the set of simplices having a face in S. Note that the star of S is generally not a simplicial complex itself. The link of S, denoted LKS, equals CL Saint S minus Saint CLS. It is the closed star of S minus the stars of all faces of S. Algebraic topology. In algebraic topology, simplicial complexes are often useful for concrete calculations. For the definition of homology groups of a simplicial complex, one can read the corresponding chain complex directly, provided that consistent orientations are made of all simplices. The requirements of homotopy theory lead to the use of more general spaces. The CW complexes. Infinite complexes are a technical tool basic in algebraic topology. See also the discussion of polytope of simplicial complexes as subspaces of Euclidean space, made up of subsets each of which is a simplex. That somewhat more concrete concept is there attributed to Alexandrov. Any finite simplicial complex in the sense talked about here can be embedded as a polytope in that sense, in some large number of dimensions. In algebraic topology, a compact topological space which is homeomorphic to the geometric realization of a finite simplicial complex is usually called a polyhedron. See Spanier 1966, Maunder 1996, Hilton and Wiley 1967. Combinatorics. Combinatorialists often study the F-vector of a simplicial D-complex delta, which is the integral sequence F0, F1, F2, Fd plus 1, display style F_0, F_1, F_2, L dots, F_d plus 1, closing curly bracket, where phi is the number of I-1 dimensional faces of delta. By convention, F0 equals 1 unless delta is the empty complex. For instance, if delta is the boundary of the octahedron, then its F-vector is 1, 6, 12, 8, and if delta is the first simplicial complex pictured above, its F-vector is 1, 18, 23, 8, 1. A complete characterization of the possible F-vectors of simplicial complexes is given by the Kruskal-Katona theorem. By using the F-vector of a simplicial D-complex delta as coefficients of a polynomial, written in decreasing order of exponents, we obtain the F-polynomial of delta. In our two examples above, the F-polynomials would be x3 plus 6, x2 plus 12, x plus 8, display style x caret 3 plus 6 x caret 2 plus 12 x plus 8, and x 4 plus 18, x 3 plus 23, x 2 plus 8, x plus 1, display style x caret 4 plus 18 x caret 3 plus 23 x caret 2 plus 8 and x plus 1, respectively. Combinatorists are often quite interested in the H-vector of a simplicial complex delta, which is the sequence of coefficients of the polynomial that results from plugging x-1 into the F-polynomial of delta. Formally, if we write f delta x to mean the F-polynomial of delta, then the H-polynomial of delta is f delta x minus 1 equals h0 x d plus 1 plus h1 x d plus h2 x d minus 1 plus h d x plus h d plus 1, display style f underscore delta x1 equals h underscore 0 x caret d plus 1 plus h underscore 1 x caret d plus h underscore 2 x caret d1 plus c dots plus h underscore d x plus h underscore d plus 1. And the H-vector of delta is H0, H1, H2, Hd plus 1, display style H underscore 0, H underscore 1, H underscore 2, C dots, H underscore D plus 1, closing curly bracket. We calculate the H-vector of the octahedron boundary. Our first example, as follows: f x minus 1 equals x minus 1, 3 plus 6 x minus 1, 2 plus 12 x minus 1 plus 8 equals x 3 plus 3 x 2 plus 3 x plus 1. Display style f x1 equals x1 caret 3 plus 6 x1 caret 2 plus 1 2 x1 plus 8 equals x caret 3 plus 3x caret 2 plus 3x plus 1. Closing curly bracket. So the h-vector of the boundary of the octahedron is 1, 3, 3, 1. It is not an accident this h-vector is symmetric. In fact, this happens whenever delta is the boundary of a simplicial polytope. These are the dense Somerville equations. In general, however, the h-vector of a simplicial complex is not even necessarily positive. For instance, if we take delta to be the two complex given by two triangles intersecting only at a common vertex, the resulting h-vector is 1, 3, minus 2. A complete characterization of all simplicial polytope h-vectors is given by the celebrated G-theorem of Stanley, Billera, and Lee. Simplicial complexes can be seen to have the same geometric structure as the contact graph of a sphere packing, a graph where vertices are the centers of spheres and edges exist if the corresponding packing elements touch each other, and as such can be used to determine the combinatorics of sphere packings, such as the number of touching pairs, 1 simplices, touching triplets, 2 simplices, and touching quadruples, 3 simplices, in a sphere packing. See also abstract simplicial complex, barycentric subdivision, causal dynamical triangulation, delta set, polygonal chain one-dimensional simplicial complex. Tucker's lemma, Spanier, E. H. 1966. Algebraic topology. Springer. ISBN 0-387-94426-5. Maunder, C. R. F. 1996. Algebraic topology. Dover. ISBN 0-486-69131-4. Hilton, P. J. Wiley, S. 1967. Homology theory. Cambridge University Press. ISBN 0-521-09422-4. Weisstein, Eric W. Simplicial complex. MathWorld.